take up the most space. And then of the bonded ones, triple bonds take up the most space this way. And then pushing out on anything else out to the sides. That's why they go out 180 degrees. Does me help?
Could you talk about more about the Coulomb's law, like the way it is on problem B on that quiz you gave us a while ago? Do you want me to read it to you?
Coulomb's law?
Yeah.
You remember the energy. This is the equation. It's not, doesn't show up anywhere on your format of your formulas. What you need to know, yeah, you kind of do. I think you do, and I think they made a mistake by not reminding you that this is an important one, by at least giving you the formula to go, oh yeah, that thing. But what you got to remember is, and you can use this to talk about attraction for electrons to a nucleus. You could use this for attraction between ions in an ionic lattice. You can use this in a lot of different ways. Where these are the charges, and this is the distance between the two charges. The closer they are, the more they attract. Also, the higher the charge, the more they attract.
Which one was the one that was K Q1 times Q2 over R squared? What was that one?
I can't remember if it's this, but I don't know if the R squared is like another derivative of this formula, or if that was a typo on my part. Like I can't.
I know there is an R squared.
Yeah, I don't. Yeah. Don't. It doesn't. The point is, it doesn't really matter as long as you just remember charge on the numerator.
Right. That's.
Distance on the denominator, and if you make the numerator bigger, then the energy goes up. So that would be like a +2 and a -2. That lattice is going to have more energy than the same type of lattice with a +1 and a -1.
So more negative E is more energy.
More negative E is a stronger energy, right? More favorable. Large negative energies are favorable.
Favorable for what? Sorry.
For any process.
Okay.
Remember, you probably remember this from thermodynamics last year. Talking about like this type of process versus which one of these shows an endothermic process?
So the first one.
Endothermic takes in energy. The bottom one,
Oh, the
right?
bottom one is endothermic exo.
Right? This one's going to take in energy. That's not, I mean, think about it. If you were to put a ball at the bottom of a hill and go, roll, it's not going to roll up the hill spontaneously. But if you give this one just a tiny shove, it'll go down. This is going to have a negative enthalpy value, right? Because if you take products minus reactants, you're going to end up with a negative number. Negative is good. This one, products minus reactants, is positive. Not as favorable.
So it's endo.
Right, this one's endo.
So if you think about it in life terms, it's better to like give things than to receive.
Better than receive that.
That's questions from chemistry.
In the spirit of giving.
So
This look, I should have this up here for my regular chem class more. This looks just like a bunch of crazy.
can we talk about?
Did I answer? Wait, hang on. Did I answer your question about Coulomb's law?
Yeah.
We're using it in a descriptive way, not to make a calculation. You're going to calculate an energy, but you're going to say, hey, you could cite Coulomb's law. This is why I think it was a mistake for them to not give you that formula, because it's a powerful tool. You can say, right, the closer these two ions are, meaning they're smaller, that's going to make it a more powerful bond. But at the same time, if you increase the size of the charge, that's going to make it a more powerful interaction.
Wait, so like with helium bonding with francium, for example, would that be a weak bond because there's so much space because francium's so big? Or?
So helium isn't going to be a good example for that. You can say like fluorine
Yeah.
and francium. It's a super electronegative. It would probably not be a it's not going to be a stable ionic compound. It would dissolve very easily. That's why group 1 and elements tend to dissolve they'll give that electron away and just dissolve it doesn't time. It's not like they're gonna, that interaction is not strong enough to withstand water. Yeah, Haley?
Okay, so on our periodic test we had last year, we had like the charge and those are the charges, right?
Right.
On the back, so that we could tell the charge in between the two to find what we're talking about right now.
Mhm.
But on these, we don't have it, so we're just looking in general, like, oh, is it oxygen, is it a 2 minus, so, and then compared to, so it's more like general, we don't have to actually calculate. Remember last year we had to like do subtraction to find it?
I'm not sure exactly what you mean, but no, I think that you need to focus on the main group elements. Like you do need to know your polyatomic ion charges. That's something that I tried to give you guys to do over the summer for crying out loud. It's not like I'm not trying to trip you up, but if you want to know, like, all right, is potassium oxide or calcium oxide going to have a stronger lattice energy, and why? That would be a case where you want to use Coulomb's law to figure that out. And that was the one that we had for a review question a while back.
Can you say the answer isn't it potassium oxide because the charge is higher? Oh wait, no.
We say calcium oxide.
Calcium oxide because the charge is higher according to Coulomb's law.
You could use that as a reason,
Okay.
right? And it'd be one of those things where it might be like a 2 or 3 point answer, and then depending on how many valid reasons you get, and providing that you don't contradict yourself, you might get a point or two just by.
What would be another reason?
You could talk about calcium ions being, because of the loss of 2 electrons being small, being smaller than a potassium ion that only lost 1 electron.
Then you can get closer to the thing.
So the distance between them is smaller. So remember, there's more than one factor. That's why I keep pointing at the Q and the R, because I want you to remember there's both of those factors.
The R is the size.
The distance between the bond.
And the Q is the charge. Okay.
Yeah.
Can we go over oxidation?
Oxidation numbers.
Wait,
Okay.
before we do
Oh.
that, since my question is just really related into this, calculating enthalpy of a reaction on the 2007 E.
Uh-huh.
I don't know how to do that. How to get the fluorine bond into the fluor.
Okay, so remember the enthalpy of the reaction. I don't want to erase anything. Enthalpy of the reaction is equal to bonds broken minus bonds formed. And there's like a huge equation that goes with this that involves sigmas and all this kind of stuff. But delta H reaction are those two things. And you have all but one piece of the puzzle. Now keep in mind that you have that reaction for that entire part up at the very top with a delta H value. Right?
Yeah.
So you have a delta H value of negative 264 kilojoules per mole. That is this number right here.
Oh, so basically it's just simple algebra. Solving for the X.
Yeah, solve for the X.
Solve
So,
for the 2 fluorines on the 3F2. And
right,
then-
so you've got a nitrogen, right, so it's like 946 plus 3 times fluorine, right, because there's 3 F2s.
Yeah.
Minus 6 times 272. And you're solving for FF. You're right, it's just simple algebra. You just gotta remember what to do. Ha 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 ha. That's all.
So that would be an example of calculating enthalpy of a reaction
Based on energy, or determining a bond energy using enthalpy of reaction and bond energies.
How do you determine bond energy?
That's what you're doing here. You're determining a bond energy using an enthalpy of a reaction and other bond energies.
Okay.
What was the final answer?
I got negative 264.
Wait, that's the.
No, sorry, negative 141.
I was about to say, that's.
141. Not negative 141. 141. Holy smokes.
Wait, it's just positive
141. I had it wrapped around down here. I just did it last period. I just did my homework last period because I didn't have the answer.
classify a bond as polar, non-polar, ionic based on electronegativity? Like, do we need to know the ranges, like 0 to 7 being?
You don't have to do any calculations, it's more what kind of element are you dealing with, how far apart are they? So you should know your metals from your non-metals first. That'll determine if it's ionic or not. And then as far as how far away the elements are from each other. Okay, Kayla, I wanted to answer your question about the oxidation state. Okay, so if we wanted to look at, if I can think of it. This. Potassium permanganate, and I say, what's the oxidation number on manganese? How do we do this? Let's review.
Oxygen minus 2.
Oxygens are always, what?
Minus 2.
-2, unless it's a peroxide. You're not gonna, I mean, you'll know it's a peroxide if it's H2O2.
And iron K is plus 1.
So you have 4 times -2, so you have an overall charge of -8. Ions are always going to be their charge unless something weird, but yeah, pretty much like metal ions are going to be their charge. This one, which leaves manganese at, no, +7. Okay, so rules. Ions are their charge. Second rule, hydrogens are always a +1. Oxygens are always a -2. Use the deductive reasoning to figure out the missing one. Elements in their standard state, uncombined, are 0.
How did you know manganese was 7?
Because I knew this one and this one. It has to add up to 0. All of these have to add up to 0,
Okay.
right? So if oxygens are always a -2, there's 4 of them, so that adds up to -8. Potassium ion has a charge of +1. 1 plus 7, that makes it work out. So in order to make that be neutral, that had to be a +7.
So the ions are the metals.
Pretty much.
In the last rule you said when a atom is alone, just like
Uncombined are in the standard state, so like any diatomic gases or metals on their own, any of this kind of stuff, you know?
Yeah.
When they're not combined with anything else. So even though there's an O2 there like that, just because there's nothing else there but oxygen, it's still a 0.
Remember
It's in the
how
standard state.
there's a test before and we're supposed to find out what called an oxidation and a reduction reaction? We have to know that on it.
You're not doing a reaction, you're not doing, I don't think so.
There was a question about test.
Right, because that was from chapter 4. I just want you to right now remember tracking oxidation numbers, and we will get back to oxidation reduction reactions when we get to chapter 17 on electrochemistry.
So basically for this, just look at a molecule and tell me which has what charge.
Right. Right, because that's how you could tell if something's oxidized or reduced. Remember, if you look at something as a reactant, and you do all of this for one, and then you look at it as a product, and that element has a lower number, you know it was reduced. And if that element on the other side has a higher number, you know it was oxidized. So that's really that's the only difference. That's like the next step with it. So if you know how to do this, you've pretty much got you can track the rest of it.
Are we doing redox reactions on the?
I don't think so, no.
So is the test like mostly chapter 8 and 9, or is it like
It's,
everything?
the problems are, but they are AP style questions in that they will have other things in there. Tomorrow we're gonna do, it is tomorrow, isn't it? Holy crap. Tomorrow we're gonna do multiple choice and reactions. And I think there's like 10 multiple choice questions and 5 reactions.
Reactions,
Like as in, write the reaction for blah, 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 blah. Like this. There's no calculator for tomorrow. No calculator at all. There's nothing, any calculations would not require the use of a calculator. Yeah,
Our other tests have all like technically been cumulative, right?
yeah.
But is this one like more so covering everything than
I feel like it is because you're starting to get to a point where the material actually logically works together in a problem. Like you're gonna probably have a problem that deals with energy generation, a reaction, a little stoichiometry, and some gas calculation. So you're gonna have some of this, some, ideal gas law, those kinds of things, and all in the same problem. So yeah, it does involve all of these things. You know what I mean? So it's not like I'm not gonna give you like a big old problem that's just stoichiometry. It's not gonna be a determine the empirical formula from combustion analysis where it's just like a big chapter 3 problem. It's like more organic in that, and I mean that like it's more natural because it's gonna talk about a process, but then it's gonna ask you like all these different things about it that kind of touch on those different areas. Is that? So read the whole question when you get to those ones. Read the whole question because it's possible you'll know parts of it right off the bat, and the other ones you're gonna be like, oh yeah. It's not gonna necessarily always be, oh, I can't do it, so I might as well just leave it blank. Some people do that. You know who you are. Okay.
Are the 5 writing formula ones like bigger problems, or is it just write the formula, or whatever you tell us? Like, is it the whole thing, or is it just write the formula and done?
What do you mean?
Like, is it,
He's asking if it's just like this.
yeah, is it just like that, or is it like complicated as the word itself?
It's just like that.
Okay.
Yes, please.
This.
Can we review energy diagrams? And I don't know what an energy diagram is.
That's what these are.
Oh, so just,
We have to draw one of those, kind of?
Yeah. You should be able to draw one or like choose the right one for a process.
What's the heat of reaction?
Like on the heat of reaction specifically on your review is they have the reaction with the delta H is negative 267. That is the heat of that reaction.
Oh.
That's what they call it. It's an enthalpy of reaction or a heat of reaction. So heat's a reaction, yeah. So talking about a reaction, you have like a delta H value, you should be able to draw an energy diagram for any process. Generally speaking, and generally, like if it's a negative 267, you would show it like this. If you say enthalpy value is negative 267 kilojoules. That would be and you can show the little bump in there or not. Typically speaking, there's a little bump because you have an energy of activation. But
Like, when you
You
were
don't
going
have
through
to
all
for
these
this.
various steps and like one time when you showed like all these steps.
you're not going to have, yeah, it's not
No,
going to
you
be
don't
that
have to do that. You
complicated.
just showed us like,
Yeah.
it has one and then it keeps off.
Right. Yeah. Okay.
So it's sort of like the other test where you just gotta kind of keep knowing where you have to